In this video, we will be applying differential equations to solve some real-world problems that involve change. Yeah. To use DEs to solve real-world problems, we first need to know how the quantity changes with time in order for us to form the DE that we can solve subsequently. These are based on observations. For example, the birth rate of a population can be said to be proportional to the population, or dx over dt is proportional to x. Some other common relations are the rate of change of the quantity being proportional to the square of the quantity, or dx over dt is proportional to x squared, inverse proportion, or dx dt proportional to 1 over x, or the change can be taking place at a constant rate. Dx over dt is a constant at a. When we remove the proportionality signs, we usually will replace it with a proportionality constant. For example, we can change each of these equations into dx over dt equals to kx, dx over dt equals to kx squared, and dx over dt equals to k over x. However, one thing to note is that in DE, when we are assigning the proportionality constant, this proportionality constant k is always a positive number. And if we were to represent some changes which are decreasing, for example, death rate of a population, we will have to use negative k as the proportionality constant instead. So for example, we can say that dx over dt is equals to negative kx if we know that the quantity x is going to be decreasing. In example 1a, we have a cup of hot liquid. Its temperature is at theta degrees Celsius, and it is going to be placed in a room where the constant temperature of the surrounding is 25 degrees. So we know that the rate of decrease of the temperature is going to be proportional to the temperature difference between the cup of water and the surrounding, theta minus 25. And based on this, we need to form a differential equation to describe the change. So we can say that the theta over dt, which is the rate of change of temperature, is proportional to the temperature difference, theta minus 25. And therefore, we need to replace the proportionality sign to change it into an equal sign. We can say that the theta over dt must be equal to negative k theta minus 25. And I have added the negative sign because I know that theta is decreasing, since the cup of hot water is going to be losing heat and thus the temperature will decrease. Usually, in DE application questions, we will be required to solve for particular solutions instead of just general solutions. And the conditions for finding the unknown constants are often hidden within the problem description. And thus, we have to identify some keywords that are used for us to calculate these unknown constants. The first keyword is the word initially. It means the value of the quantity when t is equal to 0. For example, if the question says the population is initially 5 million, that means when t equals to 0, x is equals to 5 million. This is called the initial condition, and it is usually used to find the value of the integration constant. Next, the question could also say that when t is a certain value, x is a certain given value as well. This allows us to find the proportionality constant, and usually we will find the proportionality constant only after we have found the integration constant. Another common keyword is that at a given time, there is no change. This means that dx over dt equals to 0 at that particular instant. This is also usually used to find out the value of the proportionality constant. One more keyword that is commonly used is in the long run. This means that when t becomes infinity, what is the value of the quantity? This is usually used after we have solved for the particular solution of the dE and we want to find out the eventual value of this quantity. Example 1b is a continuation of example 1a, where in 1a we have found the dE describing this problem to be d theta over dt equals to negative k theta minus 25. So we now just have to solve this dE and apply the initial conditions to find out the value of the integration constant. So let's solve the dE now. We get integrate 1 over theta minus 25 d theta will be equals to integrate negative k dt. So we have ln of mod theta minus 25 equals to negative kt plus c. And if we were to rearrange this entire equation, eventually we will end up with the form theta equals to 25 plus a e negative kt, where a equals to plus minus e to the power of c. And now we will want to find out the integration constant a over here. So we know that when t is equals to 0, theta must be 75 degrees C. So 75 equals to 25 plus a times e to the power of 0, which is 1. And therefore, we know that a must be equals to 50. With this, we can thus write down what is the particular solution. Theta will be equals to 25 plus 50 e to the power of negative k times time. And we can now sketch the solution curve. Okay, we know that the eventual temperature is going to be 25. So let's draw a dotted line for the asymptote, which is at 25. And the initial value is at 75. And this is an exponential decay curve, so it's going to look like this. And this is the solution curve for our problem. In example 1b, we stopped at finding the integration constant, and there is still the proportionality constant that we haven't found. So now we are given more hints in example 1c for us to find out what is k and solve any question that follows up. So we know that after 10 minutes, the temperature is 35 degrees. That means when t is equal to 10, theta is equal to 35. Therefore, we can substitute these two values into our earlier solution to get 35 equals to 25 plus 50 e to the power of negative 10k. And if we were to solve this equation, we will end up with k equals to 1 over 10 ln 5. Now therefore, we can say that the particular solution is theta equals to 25 plus 50 e to the power of negative 1 over 10 ln 5 times time. And next, after we obtain the particular solution, what we want is the time taken for it to cool from 75 degrees C, that means from t equals to 0 until the point where it is 30 degrees. So what we have to do is to simply substitute theta equals to 30 into our particular solution, and we will be able to find out the corresponding time. So we have 30 equals to 25 plus 50 e to the power of negative 1 over 10 ln 5 times time. So if we were to solve this equation, we will end up with t equals to 14.3 or roughly 14 minutes. So we know that the cup of hot liquid needs about 14 minutes to cool down from 75 degrees to 30 degrees Celsius. In example 2a, we now have a certain species of birds staying on a deserted island, and we know that the population is changing at a certain rate. That is, number one, growing at a rate proportional to the population. That means for the growth, the x over dt is proportional to x. Also, the birds are going to die at a rate proportional to x squared. So for death, the x over dt is proportional to x squared. So each of these can be changed into equations. So dx over dt for the case of growth becomes ax, and dx over dt for death becomes negative bx squared. Negative because, again, it is a death rate, therefore the population is going to be decreasing. And I can say that based on this growth and death rates, the overall rate of change of the population will be dx over dt equals to ax minus bx squared. Based on example 2a, we know that dx over dt is equals to ax minus bx squared. But now we see that the question wants us to show this dE instead. So there is just one unknown alpha instead of two unknowns a and b. So we have to make use of the clue given in the question in order to find out the relationship between a and b such that we can reduce one of the variables. So the clue that we are going to use now is when the population is 50, the rate of change of population is 75%, that when the population is 100. So what that means is dx over dt when x is equals to 50 is going to be 3/4, 75% is 3/4, dx over dt when x is 100. So from here, I will have 50a minus 2500b equals to 3/4, 100a minus 10,000b. Now if I simplify this equation, eventually I can show that it is going to be equals to a equals to 200b. Therefore, if I substitute a equals to 200b into my original dE, let's say I call this equation 1, this is equation 2. I will have dx over dt equals to 200b 200b x minus bx squared, which I can factorize out bx, and I'm left with 200 minus x. Now if I let b equals to alpha, I will end up with the equation dx over dt equals to alpha x times 200 minus x. And this is the equation that the question has asked me to show. In example 2c, we are now going to solve the dE that we have found in 2b in order to arrive at a solution which we are required to show that it can be written in this form. So let's solve the dE. From earlier, we know that dx dt equals to alpha times x times 200 minus x. So we can separate the variables into integration of 1 over x 200 minus x dx equals to integrate alpha dt. So to solve the integral on the left hand side, we will have to employ partial fractions, and after applying partial fractions, I will get 1 over 200 integration of 1 over x plus 1 over 200 minus x dx equals to integrate alpha dt. So I can now integrate both sides to get 1 over 200 ln modulus of x over 200 minus x equals to alpha t plus c. And if I rearrange this entire equation, I will have x over 200 minus x equals to a e to the power of 200 t times alpha, where a is equals to e to the power of 200 c. And I know that when t is equals to 0, x is equals to 10. So what this tells me is I can calculate my A value by substituting both these values in. Eventually, I will get A equals to 1 over 19. Now with this, I will have my particular solution. And therefore, let's substitute all of them into our solution. I will get x over 200 minus x equals to 1 over 19 e to the power of 200 alpha t. And next, I can do some manipulation to get 19x equals to 200 e to the power of 200 alpha t minus x times e to the power of 200 alpha t. Now if I consolidate all the x terms together, I'll get x times 19 plus e to the power of 200 alpha t equals to 200 e to the power of 200 alpha t. And therefore, I can rewrite x as 200 e to the power of 200 alpha t divided by 19 plus e to the power of 200 alpha t. But note that this is not the form that I'm required to show. What I need to show is this form over here where there is no exponential form at the top and the power for the exponential has become negative. So what I have to do now is to simply factorize out the exponential terms on the top and the bottom and cancel them out. So I will get e to the power of 200t multiplied by 200 divided by e to the power of 200 alpha t, sorry there's an alpha on top here as well, 19 e to the power of negative 200 alpha t plus 1, and I can cancel out these two terms nicely to end up with 200 over 1 plus 19 e to the power of negative 200 alpha t. And this will be the solution that they want, where P is 200 and Q will be 19.